Imagine a sky so profoundly dimmed that people actually coined a new word for it. Munkilia, the dark year. Picture summer so unnaturally cold that grapes, the very grapes in France, couldn't ripen until late October. A date so late it was just unheard of for centuries. This wasn't some scene from an ancient epic. This was the chilling reality of 1258 CE, the year after one of Earth's most colossal natural disasters. And for almost 7 centuries, the true source of this global environmental catastrophe, an event so huge it literally etched its signature onto ice, into tree rings, and within ancient chronicles, well, it remained a mystery. But today, we're going to unearth its secrets. Welcome to the Deep Dive. We take complex, cutting-edge research and distill it into powerful insights for you. Our mission today: to really plunge into the climatic and societal fallout of the 1257 CE Samalas volcano eruption. We're going to meticulously explore how this monumental event reshaped Northern Hemisphere weather, how it impacted people, and how modern science, using this fascinating blend of old records and new models, has finally started to unravel its legacy. For this deep dive, our core insights come from two pivotal studies. First, a foundational 2017 article in Nature Geoscience by Guay and colleagues. They reconstructed the climate response using proxy records.
Right, a really crucial multi-proxy approach.
Exactly. Then we pivot to a more recent, equally critical 2020 study by Wade et al. In PNAS. They tap into reconciling the climate and, interestingly, the ozone responses using advanced Earth system models. We'll also touch on some specifics from Marshall et al. On the models themselves. Our goal is simple: extract the most important insights, present them with detail and clarity so you, whether you're maybe a nurse thinking about environmental health or just curious, can get a rapid, rigorous grasp of this extraordinary event and its implications. And here's the central puzzle right off the bat. Samalas was huge, one of the largest sulfur-rich eruptions we know of in the Common Era. We're talking twice the sulfur volume of Tambora in 1850.
That's right, twice the sulfur. A staggering amount.
Yet the initial climate models, they actually struggled to predict its full impact. In fact, they often overestimated the cooling. Why? What was going on there?
That's precisely the enigma we need to unpack. This discrepancy, the massive eruption, huge sulfur load, but models predicting too much cooling, that's the core issue. It really highlighted a fundamental gap in those earlier modeling approaches. They often used, shall we say, simpler representations of volcanic forcing.
Simpler how?
Well, they often neglected the really intricate microphysical processes of aerosols, how these tiny particles form, grow, interact in the stratosphere. And they missed some of the complex atmospheric chemistry, too. Without that nuance, those models, well, they just couldn't capture the real-world nonlinear response to such a colossal injection of material.
Nonlinear meaning it's not just a simple cause and effect.
Exactly. More sulfur doesn't automatically mean proportionally more cooling, especially at these extreme levels. There are limiting factors. So resolving this discrepancy isn't just about history. It's fundamental to understanding how any massive eruption impacts climate, past and future.
Okay, let's start with the eruption itself. You called it a planetary scale disturbance. Help us grasp that scale. What metrics tell us this wasn't just a local Indonesian event?
Planetary scale is definitely the right term. Samalas on Lombok, Indonesia in 1257. It was truly exceptional for the Common Era, the last 2 millennia, basically. To put in perspective, that sulfur deposition found in ice cores, these amazing natural archives, right?
Layers of history.
Exactly. The sulfur from Samalas is estimated to be twice the volume of Tambora's in 1815.
And Tambora gave us the year without a summer.
Precisely. Tambora had clear global reach. So Samalas releasing double that sulfur. It indicates an extraordinary atmospheric event, almost hard to comprehend, really. And the volcanic metrics back this up. Sediment analysis concerns its magnitude, and Me7, VEI7.
Okay, break those down for us. Me7, VEI7.
Sure. Me is magnitude of eruption, measuring the total erupted mass. VEI is the volcanic explosivity index. It factors in volume and column height. A VEI7 means Samalas ejected at least 40 cubic kilometers of dense magma.
40 cubic kilometers? That's immense.
It's vast. Imagine a cube over 3.4 kilometers on each side. And the eruption column, the plume of ash and gas, estimated to have reached an astonishing 43 kilometers high.
43 kilometers? Way up into the stratosphere, then.
Far into the stratosphere, almost 5 times higher than a jet flies. This height is crucial. It guarantees that the volcanic gases and aerosols spread globally via high-altitude winds, not just regionally. It was a global atmospheric disruption.
So you mentioned this initial puzzle. The models predicted stronger, longer cooling than the early tree ring data suggested. Why was this such a challenge for scientists?
Yes, for about 2 decades, this was a real head-scratcher. The early climate models consistently simulated more intense, more prolonged cooling in Northern Hemisphere summers than what the initial tree ring reconstructions indicated.
Especially outside Europe, right?
Exactly. This apparent lack of really widespread, strong cooling was puzzling, because for other big eruptions like the mysterious 536 event, Putina in 1600, even Tambora, there's plenty of historical evidence for persistent dust veils and widespread cooling.
So why not Samalas, being even bigger in terms of sulfur?
That was the question. It led some to wonder if maybe tree ring with proxies weren't sensitive enough for these massive short-term cooling events.
Or maybe the models were missing something.
Precisely. It raised serious concerns about the models themselves, particularly those lacking what we call aerosol microphysical modules, the parts that simulate the detailed behavior of these tiny atmospheric particles. It became a major focus for improving the models.
Okay, so how did the 2017 Guay study start to crack this puzzle? What did they find about the actual climate response?
Guay was a big step forward. They used a multi-proxy approach, not just relying on one thing.
Meaning?
They meticulously integrated evidence from historical archives, written accounts, plus ice core data for atmospheric chemistry, and an extensive network of tree ring records for temperature data.
Triangulating the evidence.
Exactly. This allowed for a much more robust and crucially spatially detailed reconstruction of the climate response. And their findings were clear. 1258 and 1259 did experience some of the coldest northern hemisphere summers of the last millennium.
How cold are we talking?
Well, 1259 saw an average surface cooling of -1.2 degrees Celsius relative to the long-term average. That made it the third coldest summer since at least 1200 CE. 1258 was a bit less severe, -0.7 degrees C, but still the 16th coldest. And to put Samalas in context, they compared it to other big volcanic years. 1601 from Putina was also 1=1.2 degrees C, the second coldest. 1453 was 1=1.0 degrees C, seventh coldest. And 1816, the year without a summer after Tambora, also 1.2 degrees C, the absolute coldest single summer.
So comparable cooling in specific years.
Yes, but here's a really striking part. If you look at the cumulative summer cooling, June, July, August, over the 2 years following the eruption.
No, the combined impact.
Exactly. On that 2-year metric, Samalas is associated with the strongest cooling anomaly of the entire last millennium. Stronger than Tambora's 2-year impact, stronger than any other.
Wow. So a profound, sustained chill, even if one single year wasn't the coldest ever.
Precisely. It underscores a really pervasive multi-year impact.
But you also stressed this cooling was spatially heterogeneous. What does that mean practically? And why did some places actually get warmer? That seems counterintuitive.
Yes, spatially heterogeneous is key. It means the cooling wasn't a uniform blanket across the northern hemisphere. Far from it. While regions like Western Europe, Siberia, and Japan definitely experienced strong cooling, areas like Alaska and northern Canada actually saw warmer than average conditions.
Warmer? After a massive cooling eruption? How?
Seems counterintuitive, I know. The Guay study suggests that in North America, this happened because the direct cooling effect from the volcanic aerosols was overridden, or at least strongly modulated, by natural climate variability. Specifically, a positive phase of the El Niño Southern Oscillation, ENSO.
And, okay, the Pacific warming pattern.
Right. Proxy records and climate simulations suggest there's actually an increased chance of an El Niño event in the first or second year after a large volcanic eruption.
Interesting feedback loop.
It is. And when El Niño occurs, it triggers atmospheric responses that can warm certain regions, like parts of North America in this case, enough to counteract the volcanic cooling signal locally. It really highlights the complex dance between a huge external shock, like a volcano, and the Earth's internal climate rhythms.
Which leads us straight to the societal impact. The common story is often volcano erupts, famine follows. What did the research find about Samalas and the famines in England and Japan around that time? Did the eruption trigger these crises?
This is a really crucial clarification, correcting a common historical oversimplification. Contemporary records, like Chronicles, absolutely document severe famines in England and Japan during this period, but the research, specifically Guay et al., shows very clearly that these crises had actually already begun before the Samalas eruption in late 1257.
They predated the eruption.
Yes. In England, for example, the severe famine of 1258 followed 2 consecutive poor harvests in 1256 and 1257, combined with high food prices and hoarding. It was already a desperate situation, tragically leading to thousands of deaths in London alone before the volcanic winter hit.
So the eruption landed on top of an existing crisis.
Exactly. Similarly, the Shoga famine in Japan was a multi-year crisis from 1257 to 1260. The awful climate of 1258 and 1259 certainly amplified it, destroying crops, but it didn't initiate it. The overwhelming conclusion is that Samalas aggravated these existing crises. It intensified them, made them worse, but it wasn't the sole trigger.
That's a really important distinction. It's not just the natural disaster, but the state of the society it hits.
Absolutely. It highlights the interplay between the hazard, the eruption, and the pre-existing vulnerability of the population. Societal resilience, or lack thereof, is key. It's a powerful lesson for understanding historical disasters, and frankly, for preparing for future ones too.
It's a sobering reminder. Okay, let's pause for a quick recap of these foundational points. All right, so we've established Samalas in 1257 was immense double Tambora sulfur. While early models struggled, newer research confirms 1258 and 59 saw some of the coldest northern hemisphere summers in a millennium. And crucially, that 2-year cumulative cooling was the strongest in the last 1,000 years.
Right, a key finding.
But the cooling wasn't uniform, it was spatially heterogeneous. Some places even warmed, likely due to interactions with climate patterns like ENS. And finally, the big historical correction. Samalas aggravated pre-existing famines in places like England and Japan. It didn't single-handedly cause them.
Precisely. And building on that, it's vital we explicitly address and maybe correct some lingering misconceptions.
Go ahead.
First, that common narrative you mentioned, Samalas causing the famines. Guay et al.'s work clearly shows the crises started before the eruption. Samalas was a catastrophic intensifier, not the sole trigger. It really underscores how social and economic context shapes disaster impacts. It wasn't a simple A causes B situation.
All right, much more complex.
Second, the idea of uniform global cooling. Older models might have suggested that, but the Guay study firmly establishes spatial heterogeneity. Not everywhere cooled equally, some places warmed. This highlights the complexity of atmospheric and oceanic connections, how climate signals travel and interact.
So no simple global deep freeze?
Not at all. And third, that initial assumption that more sulfur automatically means proportionally more cooling a linear relationship. The data from Samalas, being so sulfur-rich yet causing cooling comparable to lesser eruptions like Tambora in individual years, really challenges that. It points strongly towards nonlinearity.
Meaning other factors are crucial.
Exactly. Factors like aerosol and microphysics, how the particles form, grow, and fall out of the stratosphere, play a huge modulating role. It's not just about the total amount of sulfur injected. This nonlinear understanding is fundamental.
That's a huge refinement and understanding. So we have the scientific data, the model corrections. But what did this feel like for people living through it? How did medieval society experience 1258, and how do those old records help modern science?
This is where history and climate science really come together beautifully.
Yep.
The Guay study involved this incredibly rigorous deep dive into 180 different medieval annals and chronicles from the 13th century.
180 sources, that's extensive.
It really is. They examined original manuscripts, edited texts, mostly in Latin, but also Old French, High Middle German, Old Castilian, a rich tapestry of voices. From these, 59 narrative sources, specifically from Western Europe, reported on weather and what we call phenology, the timing of natural events, like harvests for the key years 1257 to 1261.
So direct observations from the time.
Exactly. And what's striking is that this level of detailed documentation in medieval archives was apparently reserved only for truly extreme anomalous weather events. The only other comparable episode they found mentioned so widely was an incredibly cold winter in 123334.
So the sheer volume of records for 1258 tells us something itself.
It absolutely does. It underscores that contemporaries knew this was something extraordinary, way outside normal experience. Not just a bad year, but a historically significant anomaly.
Incredible. Can you share some of what those witnesses actually wrote? What was it like living through that summerless summer?
The consistency is remarkable. Across Western Europe, chronicle after chronicle reports the same things for 1258. Pervasive cold, constant rain, unusually persistent cloud cover.
Sounds miserable.
Utterly. And these conditions directly prevented crops and fruits from ripening. Devastating for food supplies. There's a particularly valid quote from the Norman Notes of Coutances that says, and I'm translating slightly, "There was no summer during summer. The weather was very rainy and cold at harvest time. Neither the crop harvest nor the grape harvest were good. Grapes could not reach maturity. They were green, altered, and in poor health."
Wow. Green, altered, and in poor health. That really captures the agricultural disaster.
It does. And that phrase, "no summer during summer," sounds uncannily like the descriptions from 1816, the year without a summer after Tambora. It gives us a relatable anchor point across the centuries for the severity of it.
Beyond these descriptions, were there quantitative records? You mentioned grape harvest delays. How precise can we get?
Yes, the grape harvest dates, or GHD, offer remarkable quantitative insight. Reports of poor quality grapes and very late harvests came from all over Western Europe, Spain, France, the Czech lands. But the precise dates were mainly recoverable from key regions in France: Alsace-Lorraine, the Paris area, Ile-de-France, and Burgundy.
And what did those dates show for 1258?
They're astonishing. In Alsace-Lorraine, one chronicler, Richard of Senones, reported grapes were still green and hard as stone on October 8th. The harvest was eventually postponed until the end of October, around day 305 of the year.
Late October. That's incredibly late for grapes.
Extremely. In Paris, records suggest the harvest started on day 312. In Burgundy, the estimate is around day 302. Now compare these to long-term GHD records spanning centuries. The 1258 dates were, by far, the latest ever observed in these extensive series. They were even later than in 1816. Specifically, 7 days later in Alsace, 16 days later in Paris, and 6 days later in Burgundy compared to the year without a summer.
16 days later than 1816 in Paris. That's staggering.
It really is. Statistically, using extreme value theory to assess rarity, the calculated return period for those 1258 grape harvest dates exceeds 1,000 years for all three regions.
A 1 in a 1,000-year event or rarer?
Or rarer. Compare that to about a 100-year return period for 1816. And if you exclude other known volcanic years from the analysis, the return period for 1258 becomes statistically infinite, suggesting it was virtually impossible through natural variability alone.
So strong quantitative proof of extreme conditions.
Very strong. Now, the researchers rightly add caveats. We can't perfectly account for changes in grape varieties or farming practices over 750 years.
Sure, historical data has limits.
Of course. But even with those caveats, the GHD data is an exceptionally powerful indicator of unusually cold April to September conditions across Western Europe in 1258.
Besides the impact on agriculture, did people notice changes in the sky itself? Any direct evidence of that volcanic dust veil dimming the sun?
Yes, absolutely. Compelling evidence. In Germany, the Annals of Speyer mention that people commonly called 1258 a Munkelier.
Munkelier, the dark year, or year of fog.
Exactly. And the use of this specific vernacular term, a Middle High German word, rather than just a Latin description by scholars, is significant.
Why?
It suggests the dimming of sunlight was so noticeable, so unusual, so widespread, that ordinary people gave it its own name. It wasn't just an academic observation, it was a lived reality that entered common language.
A palpable change in the atmosphere.
Precisely. And this is powerfully corroborated by astronomical observations. The Annals Amanuenses from Genoa, Italy, describe a very dark total lunar eclipse on November 12, 1258. They rated it L Cizeron on the Danjon scale.
L0 being the darkest possible.
Yes, extremely dark, almost invisible. This happens when the stratosphere is loaded with aerosols, blocking sunlight that would normally reflect off the moon during an eclipse. And this matches another known dark lunar eclipse recorded earlier that year on May 23rd in England by John de Taxter.
So multiple independent accounts of dark eclipses.
Exactly.
Yeah.
Taken together, the Munkelier term and these dark eclipse observations provide strong, independent evidence for that stratospheric aerosol veil. It points directly to a volcanic origin.
We have this incredibly strong picture from Europe. Did these echoes reach further? Was Japan the only other place with records?
Contemporary narrative sources are definitely scarcer outside Europe for 1258, but the Japanese record is significant. The Azuma Kagami, the Mirror of the East, from Kamakura, reports conditions strikingly similar to Europe, a wet, cold summer with heavy rain and strong winds.
And the impact there.
It reportedly destroyed rice paddies and gardens in several provinces, causing agricultural devastation.
So similar impacts, continents apart.
Yes. It shows the climatic consequences were felt far beyond Europe, impacting agriculture and society in regions as distant as Japan. It underscores the global reach, even if the historical paper trail is uneven.
Let's pause again for a micro recap, pulling together these historical threads. Okay, we've just sifted through some remarkable historical detective work. Medieval chronicles describing a summerless summer, those incredibly late grape harvests in 1258, even more extreme than 1816's. Plus, the common German term Munkelier, the dark year, and observations of unusually dark lunar eclipses, all pointing to a persistent volcanic veil. And critically, similar reports of cold, wet conditions and crop damage coming all the way from Japan. These historical accounts, they're not just anecdotes anymore, are they? They're real data points for climate science.
Absolutely. They provide invaluable empirical grounding, and they allow us to correct and refine some previous understanding. Well, first, that year without a summer analogy. While 1816 is famous, the grape harvest data shows 1258 was even more extreme in those specific French regions, both in delay and statistical rarity, especially since 1258 didn't have other major eruptions clouding the picture. So for agricultural impact there, Samalas holds the more severe record. It refines that comparison.
Right, a crucial nuance.
Second, the significance of a word like monciliar. Its use in common language, not just scholarly Latin, suggests the atmospheric changes were profoundly widespread and palpable to ordinary people. It's more than a linguistic quirk. It indicates the depth of the event's societal imprint beyond formal records. It tells us how deeply it was felt.
Okay, moving from historical texts back to the paleoclimate proxies. How do things like tree rings and ice cores complement these stories and give us hard numbers on the cooling?
They provide the essential quantitative backbone. The researchers use this extensive tree ring network covering the last 2 millennia, 25 chronologies in total.
What types of tree ring data?
13 were based on tree ring width, TRW, which often reflects overall growing conditions. 12 were based on maximum latewood density, MXD, which is generally more sensitive specifically to summer temperatures.
A diverse network.
Yes, and crucial for mapping the climate anomalies spatially, especially in areas where we don't have medieval texts, like large parts of Asia and North America. The methodology was rigorous. All 25 chronologies span the 13th century, and all were statistically shown to correlate significantly with summer temperatures. They used a complex, nested approach to build a robust temperature reconstruction for the Northern Hemisphere land masses, north of 40 degrees latitude.
And was this reconstruction reliable?
Very. It passed stringent statistical verification tests. For instance, the core reconstruction explained about 41% of the variance in modern instrumental temperature records over a long period, which is quite strong for this kind of paleoclimate work. And the volcanic signal itself was statistically unmistakable. A Kolmogorov-Smirnov test showed with very high confidence, P 0.01, that the temperature distributions in major volcanic years were significantly different from non-volcanic years.
So the tree rings clearly picked up the volcanic cooling.
Unquestionably. And they independently confirmed the temperature anomalies we discussed earlier. 1259 is the third coldest summer since 1200, -1.2 degrees. 1258 is the 16th coldest, -0.7 degrees C.
And the cumulative effect.
Again, confirmed. Summing the summer anomalies for 1258 and 1259, the tree rings show Samalas caused the strongest 2-year cooling anomaly of the entire last millennium. The convergence between historical accounts and this quantitative proxy data is really powerful.
It really is. Let's dig into that spatial variation again. Based on the tree rings and ice cores, which regions got hit hardest, and where was the cooling less severe or even absent?
The spatial patterns are fascinating. The tree ring chronologies were grouped into regional clusters, and they also incorporated stable oxygen isotope data from 3 Greenland ice cores, which gives temperature information for Greenland and Iceland. The data for 1258 shows severe cooling between -1.4 degrees C and -2.0 degrees C below average in Western Europe, the Canadian Rockies, Central Asia, and Siberia.
-2 degrees. That's a huge drop for summer average.
It's extreme. And further evidence comes from frost rings found in trees in Siberia and Central Asia.
Frost rings?
Yes, they're basically damage to the wood cells caused by unseasonal severe frost during the growing season. They're a well-known biological marker for abrupt volcanic cooling events.
Okay, so those regions felt it strongly. What about the others?
In stark contrast, Greenland ice cores showed only very slight cooling, -0.1 degrees C. And remarkably, tree rings from Quebec and Canada actually indicated warming, +0.5 degrees C, and Alaska showed warming too, +0.3 degrees C. Scandinavia had less pronounced cooling, -0.5 degrees.
So really pronounced differences?
Huge differences. It strongly suggests that in these less affected or warming regions, internal climate variability like El Niño patterns or maybe the Pacific North American pattern dominated the local climate, eventually overriding the direct cooling effect from the volcano. Again, that complex interplay.
And was the impact also varied in time? Did some places feel the cold later or for longer? You mentioned a lag effect.
Yes, the timing also varied. Interestingly, some regions didn't experience their maximum cooling until 1259, 2 years after the eruption.
Like Quebec.
Quebec is a good example.
Yeah.
It showed a strong negative anomaly in 1259. This seems linked to very cold conditions right at the end of the 1258 growing season, which left a biological imprint, light rings, in the latewood. This is called autocorrelated biological memory. A tree's growth isn't just affected by the current year. Conditions from the previous year, like stored energy reserves or needle formation, carry over and influence the next year's growth.
A biological lag.
Exactly. However, This memory effect can't explain everything. In Siberia, for instance, the 1259 cooling was confirmed by those frost rings and even historical accounts of July snowfall. It was genuinely extremely cold there in 1259, not just a lag effect.
And did recovery happen quickly everywhere else?
Not uniformly, but generally yes. By summer 1259, parts of North America's Pacific coast and Western Europe were already seeing milder conditions. Remarkably, the Annales Romaenses in Germany reported a hot and dry summer in 1259, with abundant wine despite little rain.
Hot and dry in 1259. That shows incredible regional variation in recovery, too.
It really does. But overall, both the tree rings and the chronicles indicate that by 1260 and 1261, the major climate anomalies had largely subsided.
So the direct impact lasted about 3 to 4 years.
That seems to be the consensus from the proxies. And this finding directly contradicted some of those earlier climate models, the ones without sophisticated aerosol physics.
Right, the ones that predicted cooling lasting much longer.
Yes, some predicted significant cooling persisting until 1264. The proxy data suggests that wasn't the case. It reinforces that point about nonlinearity. Samalas, despite its massive sulfur load, produced hemispheric cooling comparable to lesser eruptions.
Yeah.
It did not cause a year without summer everywhere, only in certain regions, modulated by internal climate patterns.
And these detailed reconstructions provide crucial benchmarks for testing current models.
Absolutely critical constraints for evaluating how well our models capture the complexities of volcanic impacts.
A powerful example of science refining itself.
Yeah.
Let's recap this section on proxies and model revelations. All right, so we've seen how this huge network of tree rings and ice cores painted a really detailed, nuanced picture of the Samalas cooling. Significant, yes, but regionally varied, and shorter-lived, maybe 3 to 4 years direct impact than some earlier models thought. It really highlights this complex dance between the volcanic forcing and the Earth's own internal climate patterns.
Precisely. And this allows us to make some really important corrections to previous scientific understanding. First, we need to be explicit. Those older generations of climate models, particularly those lacking advanced aerosol physics or using simple linear scaling, they consistently overestimated both the amount and the duration of the cooling from Samalas. The Gillis study points this out regarding earlier PMIP simulations. This is a direct correction. Those simpler models were missing key parts of the physics.
So the newer models with better physics are more accurate.
Much more accurate. Second, and is worth repeating, volcanic cooling does not scale linearly with sulfur yield, especially for these mega eruptions. Samalas having comparable cooling to Tambora despite double the sulfur proves this.
Right.
It forces us beyond a simple more sulfur, more cooling idea. It tells us aerosol microphysics, particle formation, growth, removal is absolutely critical and nonlinear. That's a fundamental shift in understanding how these massive events work.
Okay, now we dive even deeper with the weighted all study. They brought in another factor, halogens, chlorine, bromine. Why are these elements suddenly so important in the Samalas story?
Right, weighed it all. Tackled this next layer of complexity. Samalas wasn't just the biggest sulfur injector of the Common Era. It likely also released huge amounts of halogens, chlorine, and bromine gases into the stratosphere. Estimates suggest megatons.
And why is that significant? What was the concern?
The major speculation, the critical concern, is that these co-emitted halogens could have caused massive stratospheric ozone depletion.
Ah, attacking the ozone layer.
Exactly. And a depleted ozone layer means much more harmful UV radiation reaches the surface. Plus, changes in ozone can also subtly influence temperature and atmospheric circulation. It adds a whole new dimension of potential impacts beyond just the direct cooling from sulfate aerosols. Understanding this halogen-ozone link is crucial for getting the full picture of Samalas and for any future large eruption.
So to investigate this, they used a very advanced climate model, HAGEM 3ES. What made this model suitable, and how did they set up their experiments to test the effects of sulfur versus halogens?
HAGEM 3ES was key because it's a fully coupled Earth system model that includes interactive atmospheric chemistry and aerosol microphysics.
Meaning it simulates the chemical reactions and particle behavior dynamically.
Precisely. It's much more realistic than models where those things are just prescribed or simplified. It can capture the complex feedbacks. To test the halogen impact, they designed 4 distinct emission scenarios based on estimates of the total gases released, but accounting for uncertainty in how much actually reached the stratosphere.
What were the scenarios?
Okay, first, HIAL, high halogen. This assumed a plausible maximum stratospheric injection, 20% of the estimated total halogens getting up there. That meant about 142 teragrams, Tg of SO2, almost 47 TIs of HCl chlorine, and 0.26 TGavs of HBr, bromine. Remember, a teragram is 1,000,000 metric tons. Huge numbers.
Okay, a high-end guess.
Right. Second, low halogen. More conservative minimum, only 1% of estimated halogens reaching the stratosphere. So about 95 TJS SO2, just over 2 TJ and 0.013 DHBr.
A low-end guess.
Exactly. And third, crucially, both SO2, no halogens. These were baseline runs with only sulfur dioxide, no halogens included, to isolate the sulfur effect. They ran 2 regions here, HISO2, 142 TgSO2, and LOSO2, 95 TrSO2, matching the sulfur levels in the halogen scenarios.
Clever design. Allows direct comparison.
Absolutely. All simulations assumed a June 1st eruption at Samalas location, injected between 19 and 34-kilometer altitude. And importantly, they used an ensemble approach, running 6 simulations for each scenario, each starting with slightly different initial climate conditions, like ENSO state.
Why 6 runs per scenario?
To account for natural internal climate variability, the background noise of the climate system. It helps distinguish the eruption's force signal from random fluctuations. It's standard practice in robust climate modeling.
So with this advanced model and these careful experiments, did they finally reconcile the simulated climate response with the historical proxy data? Did they solve that puzzle of overestimated cooling?
Yes, this was a major breakthrough. The HADGEM3ES results, using the estimated SO2 amounts, showed excellent agreement with the tree ring temperature reconstructions for 1258.
The model finally matched the real-world data.
To a large extent, yes. It was a significant validation. It really did resolve much of that earlier conundrum where models like those in CMIP5 or CESM-LME consistently predicted temperatures much lower than the proxies showed, especially for 1259.
Why were those older models so far off?
As we discussed, it's largely down to their simpler representation of volcanic forcing. They often scaled it linearly from ice core data, without accounting for those self-limiting processes, larger SO2 injections leading to larger particles that fall out faster. HADGEM3ES, with its interactive microphysics, captures this nonlinearity much better.
So many older simulations are now considered inconsistent with the proxy data.
Effectively, yes. They overestimate the cooling too much. Now, HADGEM3ES wasn't perfect. It still had some trouble capturing the exact reduction in cooling seen in the proxies for 1259, but the overall fit was vastly improved.
And did the halogens make a difference to the simulated climate, particularly the cooling duration?
A critical difference.
Yeah.
The SO2-only simulations showed a fairly rapid climate recovery back to normal within about 3 years. But the HIAGL simulations, the ones with high halogens, they showed extended cooling with very little warming in the years following. The climate stayed cold much longer.
So the halogens seemed to prolong the chill.
Exactly. This difference in cooling persistence became a key factor in evaluating how likely those different halogen scenarios actually were.
That's fascinating. How sensitive was the recovery time to these different halogen levels? Could this help rule out the high halogen scenario?
Extremely sensitive. They looked at the return date, the time it takes for temperatures to get back to positive anomalies consistently for 12 months. In the HIAL simulations, the model showed no return to pre-eruption conditions within the 10 years they analyzed, globally or in the northern hemisphere. The cooling just persisted.
A decade or more of cooling.
In that high halogen scenario, yes. But in stark contrast, the OHAL, low halogen, and the SO2-only simulations all saw temperatures return to normal within about 6 years.
That's a huge difference in recovery time.
Massive. And this divergence allows the researchers to conclude with pretty high confidence that it's very unlikely that the huge amount of halogens proposed in the HIAL scenario actually reached the stratosphere. The climate just recovered faster than that scenario would allow.
So the observed climate recovery basically contradicts the high halogen idea.
Correct. However, the LAHL scenario with only 1% halogens, that couldn't be ruled out by the climate response alone. Its recovery time was much closer to the SO2-only cases and plausible within the proxy uncertainty.
So small halogen amounts remain possible, but large amounts seem very improbable based on temperature alone.
That's the key takeaway. The climate recovery pattern acts as a powerful constraint on the initial eruption chemistry.
Let's pause for another micro recap to digest these modeling insights. Okay, so we've seen a real leap forward in climate modeling here. Models like HADGEM3ES, with their interactive chemistry and detailed aerosol physics, finally aligned much better with the historical proxy data for Samalas, fixing those earlier overestimations of cooling.
A crucial step.
And the way the climate recovered in the simulations provided vital clues. The fact that the real world seemed to recover faster than the high halogen scenario predicted allowed scientists to pretty much rule out massive halogen injection based on temperature data alone.
Exactly, a powerful constraint.
Which again reinforces the need to correct some older ideas.
Absolutely. Two key points stand out. First, the fallacy of linear forcing. Scaling volcanic impacts simply based on ice core sulfur deposition, as done in many CMIP5 CESM LME studies, is just inappropriate for massive eruptions. It ignores those self-limiting factors. Bigger eruptions make bigger particles that fall out faster. You need models that capture that non-linearity.
Right, the physics matters.
Immensely. Which leads to the second point. The importance of interactive chemistry and aerosol microphysics. The success of Halogen 3ES wasn't accidental. It's because it simulates these processes dynamically. Models without these sophisticated modules simply can't capture the nuanced reality of these huge events. Physically based aerosol treatments are essential, not optional, for accuracy here.
Beyond temperature, you mentioned the huge potential impact on the ozone layer if halogens were involved. Remind us why the ozone layer is so critical and what did the model predict, especially in that high halogen nightmare scenario?
The ozone layer, mostly in the stratosphere, is Earth's natural sunscreen. It absorbs the vast majority of the sun's harmful UVB radiation, protecting life on the surface from severe damage. Its integrity is absolutely vital. Now, in that HIAL scenario, with massive halogen injection, the Halogen 3ES model predicted a truly catastrophic ozone response, a global mean drop of 242 Dobson units.
How much is that in percentage terms?
That represents a 75% decrease from normal levels, essentially a near total loss of the ozone layer globally.
75%, that's terrifying.
It is. In the tropics, severe depletion below 180 DU would persist for about 4 years. At higher latitudes, especially the southern hemisphere, the depletion would be even worse and last longer, potentially up to a decade. It aligns with other studies showing massive halogen inputs cause ozone catastrophe.
What about the more conservative, low halogen scenario? Still significant. And what about the counterintuitive case with no halogens?
Even the low HAL scenario with just 1% halogens still showed a significant impact. Global mean ozone reduced by 25% and 81 DU drop 2 years after the eruption. Tropical depletion occurred for a year, and southern hemisphere declines persisted up to 6 years. So even small halogen amounts matter.
Okay, still concerning.
Definitely. But the truly fascinating part is the SO2 only scenario. With no halogens, global mean ozone actually increased by about 4% at its peak.
Increased. How does adding sulfur increase ozone?
It's complex atmospheric chemistry feedback. Two main things happen. First, the sulfate aerosols heat the stratosphere, which strengthens the Brewer-Dobson circulation, the slow upward movement of air in the tropics and downward at the poles. This redistributes ozone. Second, chemical reactions on the surface of the sulfate aerosols effectively tie up reactive nitrogen compounds. Since nitrogen compounds normally destroy ozone, reducing them actually leads to less ozone destruction, hence a net increase in this scenario.
Wow. So the effects are really complex and depend heavily on what else is injected alongside the sulfur.
Absolutely. It shows you can't just look at sulfur in isolation.
And do halogens also affect the sulfur chemistry itself? Like how long the SO2 stays up there or the aerosol particles?
Yes, they do. The presence of halogens fundamentally changes the oxidizing environment of the stratosphere. This, in turn, affects the lifetime of SO2, how quickly it converts to sulfate aerosol. The model calculated the SO2 e-folding lifetime. In the HIHAL case, it was 102 days, significantly longer than in the Aloha or SO2 only cases, which were around 62-68 days.
So high halogens make the SO2 stick around longer.
Effectively, yes, which impacts how and where the aerosols form and how long they persist. Halogens also subtly change the aerosol properties. The HIHAL case actually had a lower peak aerosol mass than the HISO2 case and slightly smaller particles. It's complex chemistry. But importantly, the particle sizes predicted in all scenarios were within the range known to cause significant climate cooling.
Okay, so how does all this complexity, ozone changes, aerosol changes, translate into the overall energy balance, the radiative forcing that drives the climate change?
Right. The bottom line is the net energy budget at the surface. While the high sulfur scenario, HISO2, had the biggest initial dip in incoming solar radiation, that's only part of the story. When you account for all the energy fluxes, long-wave radiation going out, heat transfer remarkably, all the scenarios showed a similar total negative energy balance, similar initial cooling effect in the very first year.
So the immediate punch was similar regardless of halogens.
Broadly, yes, but the duration was different. The HIHAL scenario showed that negative energy balance, the cooling effect, persisting significantly longer, up to 4 years.
Why longer?
Because while the sulfate aerosols rain out relatively quickly, within a few years, the halogen chemicals themselves and their impact on ozone can persist in the stratosphere for longer, continuing to affect the energy balance even after the main aerosol cloud is gone. So halogens extend the cooling period.
This brings us back to the potential health impacts, especially relevant for nurses and public health folks. If that high halogen scenario had happened with massive ozone loss, what would the consequences of the increased UV radiation have been? And does history back this up?
This is critical. Massive ozone depletion means a massive increase in surface UV radiation. The model predicted that in the HIAL scenario, large parts of the world outside the tropics would have experienced high or extreme UV levels for 4 straight summers until 1261.
Extreme UV for 4 years. What does it do to people?
Severe effects. Immediate immunosuppression, making populations far more vulnerable to infectious diseases, acute eye problems like conjunctivitis, snowblindness, and long-term dramatically increased risk of skin cancers and cataracts. Understanding this potential link between environmental events and health vulnerability is key.
But did we see evidence of this in the 13th century records? A plague of blindness or sickness lasting till 1261?
That's the crucial question. And the answer appears to be no. While famines themselves cause immunosuppression and increased disease, the historical death tolls recorded in Europe and Japan, though high initially, actually dropped significantly in 1259 and returned towards normal by 1260.
So the population health seemed to recover before 1261, when the extreme UV was predicted to end in the HIHAL model.
Exactly. That timeline mismatch is strong evidence against the HIHAL scenario having occurred. The observed relatively rapid recovery in mortality doesn't fit with 4 years of extreme UV stress.
What about the low halogen scenario? Did it predict dangerous UV levels?
It still predicted high UV near the equator for about a year, and medium UV at high latitudes for 3 years. Still potentially impactful, but unfortunately, we lack detailed historical health records from equatorial regions for that specific period to confirm or deny it.
And the obvious question, why no reports of widespread skin cancer later on, if UV was elevated even slightly?
That likely comes down to the harsh realities of 13th century life expectancy. It was much lower than today. Working classes, especially outdoor laborers most exposed to UV, often didn't live long enough for late-onset conditions like skin cancer to become prevalent. Tragically, many likely died in the famines exacerbated by the eruption before any long-term UV effects could manifest.
A grim picture. So the conclusion on halogens.
While we can't find a direct, conclusive signal of ozone depletion in the historical health records, the mortality data strongly argues against the high-level halogen injection. Small injections, like in OHAL, remain possible, but current evidence can't definitively rule them out.
Given all these complexities and findings, what are the big takeaways for future climate modeling? How does Samalas inform how we study past and future climate?
The implications are substantial. First, future big modeling efforts like CMIP6 and its PASS 1000 project, looking at the last millennium, must use improved representations of volcanic forcing, like better stratospheric aerosol optical depth (SEOD) datasets. It's a necessary step up from older approaches.
Okay, better input data.
Second, continued caution is needed with models like CE Samalas when looking at this period. As Wade et al. Showed, it consistently overestimates the Samalas cooling compared to Proxies because it uses a simpler, non-interactive aerosol scheme. While useful, its results for the 13th century need careful interpretation. Ideally, future studies should prioritize models with that more physically based interactive aerosol treatment like HAGEM3ES.
So prioritize the more sophisticated models for these events.
When possible, yes. And finally, and this is crucial for scientific progress, transparency. Modelers absolutely need to provide detailed descriptions of exactly how they implement volcanic forcing in their simulations.
Why is that so important?
Because without knowing the details, how they handle aerosol size, radiative effects, etc., it's incredibly difficult to meaningfully compare results between different models, even if they use the same input data. Clear documentation is essential for robust comparison and for the field to move forward reliably in understanding both past and future volcanic impacts.
That makes perfect sense. This has been an absolutely fascinating journey through time, geology, and climate science. Let's try to boil down the absolute key takeaways from this deep dive.
All right, let's hit the main points, flashcard style. Samalas eruption. 1257 CE. Indonesian volcano, largest sulfur injection of the Common Era, roughly 2x Tambora. A massive VEI-7 event.
Got it. Huge eruption.
Climate impact. Caused widespread but definitely spatially heterogeneous northern hemisphere cooling in 1258-1259. Crucially, the strongest 2-year cumulative cooling anomaly of the past millennium. A sustained chill.
Spatially varied, strong 2-year impact.
Okay. Historical evidence. The term Monilia, dark year, in Germany, plus unprecedented late grape harvests in Europe, over whole 1,000-year return periods, confirm extreme conditions and atmospheric dimming. Records from Japan show impacts too.
History matches the science.
Model evolution. Early models like CMIP5, CESM, LME overestimated the cooling, mainly due to simplified aerosol physics and linear forcing assumptions.
Older models got it wrong.
Advanced models. Hadgem 3ES. Newer models with interactive chemistry and aerosol microphysics achieved much better agreement with proxy data, resolving the earlier puzzle.
Better physics, better results.
Halogen debate. Large halogen injections, HIACL scenario, are very unlikely, contradicted by climate recovery patterns and historical mortality data. Small injections, LHA, remain possible.
Big halogen impact unlikely, small maybe.
Ozone depletion in UV halogens would cause ozone loss, increasing surface UV. Potential health impacts include immunosuppression, eye diseases, maybe long-term cancer risks, though historical evidence is indirect and complicated by low life expectancy.
Ozone UV link is real, historical proof tricky.
Societal link. Samalas aggravated pre-existing famines. It wasn't this whole trigger. Shows the interplay between natural hazards and societal vulnerability.
Disaster amplifier, not initiator.
Future research emphasizes the need for physically based aerosol models and total transparency in how volcanic forcing is implemented in future climate simulations.
Need better models and clear methods going forward. Excellent summary. And just to reinforce those points, let's try a few multiple choice questions, thinking conversationally. First up, which eruption dumped the most sulfur into the atmosphere in the Common Era? Was it, say, Vesuvius, Tambora, Samalas, or maybe Pinatubo?
Based on everything we've discussed, that would have to be Samalas in 1257 CE. Option C.
Right. Now, how would you best describe the cooling after Samalas across the Northern Hemisphere? Was it uniform everywhere, maybe just limited to North America, spatially heterogeneous with some warming, or only over the oceans?
Definitely spatially heterogeneous, with some regions even warming. So option C again. It wasn't simple cooling.
Okay. What was that unique medieval German word people used for the dim, foggy conditions in 1258? Was it annus obscurus, Monciliar, the Great Mist, or fog year?
That distinctive term was Moncalier. Option B tells you how much people notice the dimming.
It does. And those French grape harvests in 1258, how did they compare quantitatively to 1816, the year without a summer? Were they earlier, about the same, significantly later and more extreme, or maybe unaffected?
They were significantly later and statistically much more extreme than 1816 with those incredible 1,000-year return periods.
Yeah.
So option C, more extreme than the classic example.
Got it. Which type of climate model proved much better at simulating the Samalas climate response, fixing those earlier overestimations? Was it models with simple forcing, models without aerosol physics, models with interactive chemistry and aerosol microphysics, or those older models predicting longer cooling?
It was the models with the sophisticated interactive chemistry and aerosol microphysics, like Hadgem 3ES. Option C is the key advancement here.
Makes sense. Finally, thinking about health. What's a major potential impact linked directly to increased UV from ozone depletion, as discussed with the halogen possibility? Increased heart disease, immediate immunosuppression and eye issues, respiratory problems from ash, or better nutrient absorption?
The direct link discussed was immediate immunosuppression, making people more vulnerable to infection and acute ocular diseases. So option B.
Perfect. So let's wrap this up. What does this incredible deep dive into an eruption 750 years ago really mean for us today? Whether you're a nurse or just someone listening, what's the takeaway?
I think the powerful demonstration of interconnectedness, isn't it? How an event deep within the Earth can ripple through the atmosphere, affecting climate globally, impacting agriculture societies, even potentially human health via complex pathways like ozone chemistry. Understanding these past events through this painstaking science combining geology, history, chemistry, modeling, it's not just history. It's about refining the tools we use to understand our current climate, our future risks, and the cascading effects of extreme events.
And for healthcare professionals specifically?
The discussion around UV, immunosuppression, the link between climate shocks and public health crises like famine and disease.
Yeah.
It offers this unique historical lens on environmental determinants of health. It shows how profoundly environmental events can shape human vulnerability, a lesson that's timelessly relevant for public health preparedness today.
And for everyone else.
I think it highlights the scientific process itself beautifully. The challenge of piecing together evidence from tree rings, ice cores, medieval texts, the way models evolve and get better, the
Yeah.
constant refinement of our understanding. Science isn't static. It's this ongoing process of discovery and correction.
It really is. So here's a final thought to leave everyone with. If this single eruption from over 7 centuries ago holds such profound lessons about atmospheric chemistry, climate sensitivity, even subtle clues about historical health crises, what lessons are waiting in our present environment? How might understanding Samalas better equip us for future natural events and for the evolving global health challenges we face right now? As we've seen today, the deep dive into the past really does continue to illuminate the path forward.